All right, so if I exert a force on a wheel and it's rolling smoothly, this velocity of the center of mass, if it's constant, okay, or actually at any point in time, will be related to this equation. And if we take the derivative with respect to time on each side, we can see that we'll get the acceleration of that center of mass is equal to that. Still, only when rolling smoothly. We'll define r as the radius of that object. Now, as that object is moving at a constant speed or accelerating, this point P is moving at the same rate as its center of mass. Point P will always be the point directly under its center of mass. So as the center of mass changes position, so does point P. Does that make sense? So if we use that this has a velocity at any point in time, point P is going to have that same velocity because it has to move together. Point P is just the point of contact between the rolling object and the surface. In order for that to be rolling smoothly, the tire or wheel, whatever it is, cannot slide at point P. So since there is no sliding, what kind of friction is acting there if it's accelerating? If there is no sliding between the wheel and the surface, what type of friction exists there if the object is accelerating? How many types of friction are there? Well, at least we talk about, there's two. They are static and kinetic. So if there's no sliding between the surfaces and the wheel, it's static. So at point P, when rolling smoothly, you have static friction. The wheel is stuck to the surface at that point. There is no relative motion, which is side to side, okay, motion at point P. So what's really happening? So if we were to just kind of look at say it's a tire, here's point P, and that is moving this way. So what are the particles doing? So what is this particle of mass doing at that point in time? All right. So at that point, it's right above point P. All right. It's any series of particles there. What direction is it going to move the instant after, with relationship to point P, immediately after that point in time? It's going to move up. Only at that point with respect to point P. Anything on this side, because point P is moving to the right, it's going to move kind of underneath it. This is just moving down at the point in time. Now, it's really only occurring at this location. So it's the instantaneous position, all right? At that position, the particle is going to either move up or down at that point because point P is moving underneath it as those other particles are moving up and down. So it makes sense that if a particle is here and then a particle ends up down there, that it moved downward, right? So it's tough to imagine what's happening with respect to that point P because we're not really looking at a certain length of time. So any particle right here, as soon as it starts to change its linear position and angular position, it just moves up at that point. And that's the way you have to think about what's happening with the particles, so that there's no sliding or no relative motion at all. Now, happens when it's rolling smoothly. If it wasn't rolling smoothly, then the wheel would slide left or right, and therefore there would be some type of relative motion between the point here and there. Okay? So this point would be sliding maybe backwards, okay, at point P. But since it's stuck, it can't. All right. So if there is a force being applied to that wheel, so I know we can't see that on the video, but so if I apply force this way, we can see that there is going to be a rotation, and it did accelerate. Is friction necessary in order for that to happen? Yes. Why? It wouldn't say the rotate, because there would be nothing to create a torque. The friction is necessary to create the torque to cause the acceleration in the angular direction. If there was no friction, it would just do this. Right? All right? So there has to be friction in order for there to be an acceleration. Does there have to be friction in order for a wheel? We would have to look at the instant in time when it's already rolling. Does there have to be friction to be rolling at a constant speed? While it's moving at a constant speed, not when we looked at how to get it up to a certain speed. So let's look at this simulation here, because of course we cannot replicate what's happening. All right. Okay, so here's our object, starting right there. And we have 3 surfaces. So let's see what's going to happen if I click play on the video. So you can see it starts to roll down that ramp. All right. Now it's going to cross the green section. Does anything look out of the ordinary there? No. Okay. So the linear distance that it travels makes sense with its rate of rotation, right? And over that entire period of time, there is no change in the rate of rotation. But then you see as we go up the blue ramp, the rotation rate never changes. However, it's sliding. There is no friction on the blue surface. Therefore, the rotational rate does not change. And what's happening over the green surface? So is there friction on the green surface? Did the rate of, can you guys see that clear enough? Did the rate of rotation change? No. So there is no friction on the green surface. So is there friction necessary to have an object roll at a constant speed? No. And it will roll as if there's friction or if there's not. If I added friction to the green surface, nothing would change. It would still roll and make sense. All right, as long as it's rolling at a constant speed and rolling smoothly. Because there will be no tendency for that wheel to slide because the particles are just moving up and down. If we need to see that, I'll put that up on the computer, okay? Because I don't have this program on the iPad. All right. So maybe we need to see that. So I'm going to end this one